Morning, everybody. How y'all doing out there? We're not doing too bad here. I have a DC drive right here. It's manufactured by Groschopp, and it's model number type R41.1 1Q. The problem with this drive card is that the motor was running away. There was no speed control. And what I found bad on this was that on terminal 14, that's our tach/armature feedback input. And the trace from that terminal board to the input resistor opened up. So they must have had a spike on that tach or armature feedback of the motor. So after I got that trace repaired, it runs good. Now here's my hookups, and I'll put these hookups at the end of the video and also show you some drawings that I made, my schematic drawings I made of this board right here. Now, that's how I found that open trace. Was I was mapping the SCR diode bridge rectifier circuit, the LM324 circuit, the power supply circuit, and the terminal board connections coming in. And when I got to terminal 14, I had no continuity. I could see what I thought was a trace, but it wasn't. It had opened up to that input resistor right there. So let's plug this in to my hookups. Now, this transformer right here, the primary winding of the transformer where L1 and L2 come in, the transformer label says that it's a 230 volt AC transformer. But if I apply 120 volts AC to L1 and L2, the plus or minus 12 volt regulators, they still come up good. So instead of using the high voltage of 220 volts AC single phase, I'm going to use 120 volts AC right there. Let's go ahead and power it up. Now, I'm going to jump terminal 13 to terminal 18, that's our enable. Increase the speed. We should see these light bulbs come on real quick. There you go, look at that. It's working really fine. Sweet. Y'all fixed another one. So you can go back into the machine and do a little bit more work. Let me turn this overhead light off here so you can see those light bulbs. Nice. That's awesome. Now we're going to look at the LM324 operational amplifier with the oscilloscope that my brother Jeff sent me. And we'll see some of the waveforms. That is nice. I could play with this all day long. Okay, when I get to the house, I'll show you my drawings of this circuit right here. I don't have it completely mapped out, but I have the basic functions of this DC drive mapped out. That is nice. That is really nice. Okay, we'll see you when we get there. Power down. Okay, here we are. Now, I thought I'd go over my drawings before we looked at the oscilloscope waveforms of the LM324. That way you'd have kind of an idea of what we're looking at. Now right here, this is where the line voltage comes in. I used 120 volts AC, but the drive's probably rated for 220 because that's a 220 primary winding of this transformer. But it powered up good with 120 volts AC single phase. So we are stepped down and rectified through this transformer and bridge rectifier. And we have out here a measured plus 12 volts DC and minus 12 volts DC. That's for the operational amplifier, the LM324. There's some Zener diodes that regulate the output of the bridge rectifier down to plus or minus 12 volts DC, but I didn't draw those in there. Here we have another bridge rectifier down here, and that makes the field voltage, the field inside the motor. Now F and G, let's go over here. F and G are the line input to the SCR diode bridge rectifier. Here's F, L1, and G, neutral. The output of the SCR diode bridge rectifier goes to terminal 12. And the ground side of the bridge rectifier, this is the positive side, the ground side of the bridge rectifier goes to pin 11, terminal 11. Now, this is very confusing, and I probably have this wrong, so take this with a grain of salt. But I looked at it, and I looked at it, and I looked at it, and this goes to center tap ground, center tap of this transformer back here, right there. This point and this point are the same. And I saw the trace. I saw it. It was a thick trace. But I wouldn't do it that way. There's a 0.22 ohm resistor at 22 watts right here. And the output of the two SCRs also goes up to terminal 7. This is where your positive side of your TAC generator would connect terminal 7. We'll show you the other side in a little bit, where the negative side of the TAC connects. A and B are the gates of the SCRs. That still bothers me. Maybe it's current sense. Maybe that's why this resistor right here is current sense, and I got it drawn wrong. Can we ignore that? So A and B, the gates of the two SCRs, they go over here. We're going to get a little bit complicated here. Here is A and B, and they connect to this 2N1316 CAN transistor, the emitter, through these two 130 ohm parallel capacitor and resistances right here, 130 ohms. So when the PWM is driven into the base of this transistor right here, it PWMs the gates of the SCR so that the output is pulse width modulation. The collector of the CAN transistor is tied up to plus 12 volts DC through this 100 ohm resistor. The enables, we'll get to the pulse width modulation in just a little bit. That's fairly complicated, but the enables, we have the collector of this BC547B connected to the base of the 2N1316 CAN transistor. They're both NPN. The base and collector are also connected to this operational amplifier, the LM324, pin 1 through this 10 kilo ohm resistor. Now we have a sawtooth on pin 2. I'm getting sidetracked, but it's all tied together. The sawtooth goes to pin 2, and the speed reference and the summed tact feedback eventually end up on pin 3. So this output will be pulse width modulation, and it is shunted to ground through this BC547B, so it never drives that 2N1316 base emitter junction. So we're shunted to ground when this is turned on, and it is turned on through this pull-up resistor in the collector of this BC547B, this NPN transistor. So when this transistor is off, this 5 volts turns the base emitter junction of this transistor on and turns that transistor on, driving it into saturation, so that the PWM on the output of the LM324 is shunted to ground through the collector emitter junction of this transistor. Well, how do you get this circuit to turn off? We go back this way, and we have these terminal 18 and terminal 13. They're labeled RSP and RSP on the board. I don't know what that means, but I'm going to call it enable and plus 12 volts. So we have plus 12 volts up here that goes to pin 13 through this 15 kilo ohm resistor. When this circuit is open, then the base of this transistor is pulled to ground through that 10 kilo ohm resistor, and that turns this transistor off, so that the plus 12 volts DC is applied to the base of this transistor through this 10 kilo ohm resistor, pulled up to plus 12 volts DC, turns this transistor on and shunts the PWM to ground. Now when we jump terminal 13, which is plus 12 volts DC, to terminal 18, now the positive voltage is applied to the base of this transistor, turning it on, and now this point right here goes to ground through the collector emitter of this transistor and turns this transistor off, because you would have 0 volts right here. I drew this in backwards, I got confused. Okay, so where does the speed reference come in? Let's go get that. Here we are. And we're going to be all over the place on this one. The speed reference comes in on terminal 17. And terminal 17 voltage is applied to pin 12 of the LM324. Now I couldn't find it, but there has to be a feedback resistor right here, but I could not find it. I'm going to draw one in here. It's going to look a little sloppy, but you'll get the idea. I could not find that resistor, but it has to be there someplace. And so what we have is a non-inverting amplifier right here. This would be our input resistor, and this is our feedback resistor. And so the reference voltage, let me show you where the wipers of the pot go here real quick. Right here on 16, you apply the wing of one of the potentiometer to 16. Here's our min speed pot. You apply the other wing of the potentiometer to pin 15, and that's plus 15 volts, so, or plus 12 volts. So 12 and 0 volts, if that pot's set to 0 volts, to 0 ohms. So here we have a 0 to 0 to 12 volts, pretty close to it, at this point right here. And it goes to pin 12, the non-inverting input of this operational amplifier. And the output goes to D. Now, I'm missing some components here. I don't have this whole thing drawn in right here, so it looks a little bit confusing. But D, let's go find D. D is down here. It goes to the input of this non-inverting amplifier, LM324 on pin 10. And the output goes to C, which is back up here. At this point right here, we'll go from 0 to 10 volts. And that is compared to the sawtooth waveform on pin 2. So that's where we get our PWM. If 3 is way up here, then we would have an output that's always high. If 3 is in the middle, we'd have some square wave, a 50% duty cycle. If pin 3 is way down here, the voltage, then we'd have a duty cycle that's less than 50%. And with this jumped, this is off, this transistor's off, so that PWM is no longer shunted to ground. And it is going to PWM the gates of the two SCRs with this CAN transistor 2N1316. Okay, the feedback. Oh, okay. The feedback. Where is the feedback? Oh yeah, here we go. The feedback comes in on 14, that's G minus. You remember pin 7 was G plus, here's G minus. That goes through a 150 kilo ohm resistor that's on a couple of posts, so you can change out that resistor by unsoldering the leads of that resistor from the posts. And where's E? Oh, we're back over here again. This is the summing point. So I think around this resistor right here, there must be our capacitor, there must be some resistance, because E comes in here. This is our max speed of potentiometer. E comes in here, this is the feedback. It comes in here, and I'm thinking there's some resistance around this. I couldn't find it though. So I'm going to draw a little resistor in here. Oops, no, not like that. Let's go out a little bit more. I'm pretty sure there has to be a resistor there, because this is a steady voltage and this is a capacitor. To apply a voltage through a capacitor, it has to be like a waveform. So we come in through here and we get summed to the speed reference coming in. This is a summing point. Let me see if I can draw it upside down. Sum. I'm upside down. So speed reference through here, a speed pot through here, and that is amplified out to D. Okay, there's one other thing, one last thing. How is the sawtooth derived? Well, here is L1, and here's neutral. I'm upside down again, I might draw that backwards. And they are rectified. The AC coming in from the line is rectified, but not filtered. So you have full wave rectification right here. That's applied to pin 6 of the LM324. This point right here is 1 volt. So what you have at the output, we have this waveform right here. What you have at the output is pulses going high from -12 to +11 at 120 hertz. And that goes over here. And there's some resistance and capacitance, and so what you have, and there's probably more resistance and capacitance here than what I've got drawn out. But by the time it gets from pulses here to here, we have a sawtooth. Okay, that's everything. Now we can look at the oscilloscope waveforms while we're running those light bulbs. I'll put the hookups that I have at the end of the video. There's two ways to hook this up. You can have armature feedback and tack feedback. We looked at tack feedback on G plus or G minus and G plus terminals, terminal 7 and terminal 14. But you can have tack feedback or armature feedback also if you don't have a tack. Okay. That's my drawings. Some of it confusing, some of it missing, not drawn in, but we got the gist of it. We got the idea of what's going on there. Phew. Okay. See you in a little bit. Let's take a look at pin 7. This is that base frequency that sets everything up. And we have a plus 11 volt to minus 12 volt pulses of about 120 hertz. That's pin 7. Here's pin 6. This is the output of bridge rectifier number 1. Here's pin 5. Pin 5 sits at about 1 volt. Okay. Now, what we'll look at next we'll look at pin 1. Now, pin 1, based upon where our speed potentiometer is set, will give us pulse width modulation. I'm increasing the output to the motor, and you can see as I increase the potentiometer, we have pulse width modulation. Right there is max speed out to the motor. We're slowing down, and there's min speed. Let's go look at pin 2. Pin 2 is the sawtooth, and that sets our PWM based on where pin 3 is in relation to pin 2, the sawtooth. Let's go look at pin 3. Right now, we're at 0 speed out to the motor. I'm increasing the potentiometer. Right there is max speed. Slowing down, and now the motor stopped. Let's take a look at pin 14. Right now the motor is stopped. And we're increasing the speed to the motor. There's max speed. The motor is stopped. Let's go look at pin 13. Pin 13 does not do much when I increase and decrease the speed to the motor. Here's pin 12. There's a little bit of action on pin 12. We'd have to look at the differential voltage on the inverting and non-inverting inputs to see what that output is derived from. Okay, let me slow down. Pin 8. Let's look at pin 8 again. Increasing the speed out to the motor. Decreasing. The motor stopped. Speeding up. Slowing down. Now, output of that operational amplifier, pin 8, goes to pin 3 of the operational amplifier. Here's pin 9. You can see a little bit going on there. A little bit increase. Up to about half a volt maybe. Slowing down. Stopped. Here's pin 10. Very little action. There is something going on there, but very little. Again, we'd have to look at pins 9 and 10, the inverting and non-inverting differential voltage, to see how that output is derived. Okay, let's look at VCC of the operational amplifier. Here we have about plus 12 volts. That's pin 4. Here's pin 11. That's minus VCC of the operational amplifier. That's about negative 12 volts. Okay. Now let's look at the armature feedback. Here we're stopped. We're increasing the speed to the motor. It's interesting, it goes negative. That's max speed right there. And that's about, negative 7 volts with ripple. We're slowing down. This would be our armature feedback. Stopped. Increasing speed. We're at max speed right there. Okay, that was interesting. We have a good running drive right there after we fix that trace on what was that, terminal 14, that blown trace. Okay, when I get to the house, we'll look at the paperwork. We'll see you there. 일어나! 여보, 일어나! I was taking a cat nap, and when I woke up I said, 일어나! And I hadn't heard that since 1986, 1987 when Jesus would wake me up in dark 30 to go to work. 일어나. And she had boiled a pot of water so I could wash my face before I head out. 일어나. 일어나. 여보, 일어나. The funny things we think of in our youth. Okay, so here we go. Let's talk about the hookups. This is the run info for the Groschopp DC drive type 41.0 1Q. 41.1 1Q. Now this is also for the ARI 205, I think it is. Same pinouts, just the board is laid out different. Here on terminal 3 and 4, I applied 120 volts AC single phase to 3 and 4, that's L1 and N. And that powered up the board's power supply fine. The primary of that transformer's 220 volts AC single phase, but it'll come up okay with 120 volts AC. Let's go down and look at the rest of this board. Here on terminals 9 and 10 are the field connections of that motor. Now if you have a permanent magnet DC motor, you don't need to hook up a field. But on a DC motor that has field connections, you have to hook up these connections right here. Here are the armature connections out to the motor, A plus and A minus. A plus, armature plus on terminal 12, armature minus on terminal 11 of that terminal board. Now I use light bulbs. I use 2 series 100 volt, 100 watt light bulbs for between 11 and 12. Now, in armature feedback connection, you will take terminal 11 and jump it to terminal 4. Now normally, I'll show you in a little bit, normally with an actual motor, you would have an inductor in this circuit right here. I'll show you that in a little bit. But since I wasn't using an inductor and a light bulb load, light bulb being a resistance load, I connected 11 to 14. The enables on terminal 18, that's our enable input. And I tied a switch from terminal 18 up to terminal 13. And when I enable, when I close this switch right here from terminal 18 to terminal 13, that drive will get up and go. The potentiometer for speed reference, to speed that DC motor up and slow that DC motor down. On terminal 15, that's our plus V pot. And on terminal 16, that's 0 V pot. 0 V pot going to ground through a potentiometer so that we can set the min speed. So the wings of the potentiometer tie 15 to 16. One wing here, one wing there. The wiper of the potentiometer goes to terminal 17, VREF in. Now let's go look at the different ways we can set up that tack feedback and that armature feedback with the motor. This top diagram right here, this shows how to set up your DC motor with armature feedback. Now we have A plus terminal going to the DC motor on this side right here. The other side of the DC motor goes to the A minus terminal, A plus on 12, A minus on 11, through a power choke and armature feedback being applied to pin 14 on the G minus terminal. Now if you're using tack feedback, your tack generator, tacho generator, connects to terminal 14 G minus, and the other side of the tach to terminal 7, G plus. There you go. That's how you hook up your Type 41.1 1Q or ARI 205 DC drive cord. Alright all. Thank you very much for stopping by.